Hello all of you. Welcome to the 54th lecture on the course on analysis and modeling in chemical engineering. In this week, we have been discussing about the computational methods of solving separation problems, particularly cascades. We began with the equilibrium based methods and we discussed the different kind of equation tiering approaches such as BP method and SR method. Then we also discussed the Newton-Raphson method, which is solving all the equations together. And then finally, we also discussed the inside out method, where we use the approximate relations in the inner loop of iterations and then the complex thermodynamic models in the outer loop. So now we will switch gears and talk about something that we have kind of avoiding until so far, that is the non-equilibrium effects, right? So in reality, the fundamental assumption that we have made that in every stage you have a condition of equilibrium is actually difficult to meet, and in most practical situations the stage that you have in a typical separation process will not only be not in the equilibrium but actually will be far from equilibrium. So therefore, we are going to first discuss the approaches which are based on approximations of whatever treatment that we have done for the equilibrium problems in order to also include non-equilibrium effects. But then we will discuss a more formal treatment for what is known as the rate-based model. So in I would say classically, the first approach that came into existence to include the non-equilibrium effects is to include a notion of this tray efficiency, right, and something called Murphree tray efficiency, which is still being used quite a bit. What we say here is, in the typical situation that we have discussed so far, we assume that my Kij is basically a ratio of my Yij and Xij, or I can use Yij as something like Kij multiplied with Xij. That is what we assume for equilibrium. But in reality, when we have a departure from the equilibrium, we are going to have the mole fraction in vapor not given by this particular relation, right? But even in that case, I can still define an equilibrium mole fraction that can be obtained by applying this particular relations. For a given liquid mole fraction of component I can compute what is going to be the mole fraction of vapor in the equilibrium condition. Let us take that value as Yij star and then define some kind of an efficiency, that is my actual Yij minus the Yi for the stage below it, Yij plus 1, divided by the equilibrium value which I obtain from this particular relation minus the actual value which I obtain for stage j plus 1, right. And now for the Yij star, I can substitute for this Kij Xij, right. So it is some kind of, we are looking at the departure from the equilibrium thing, right, when this Yij will be equal to Yij star. That means we have a condition of equilibrium, and in that case the tray efficiency will go to 1. But when this condition is not true, then this Murphree tray efficiency can be anything but 1, right. So therefore, it kind of includes the deviation from the equilibrium, so as to speak, right. It turns out that although it is used quite a lot, it is actually adequate only for either the binary mixture or very close boiling, that is having a similar boiling point, ideal or non-ideal multi-component mixtures, right. If it's like narrow boiling range, in that case it may work for, I would say, an ideal multi-component mixture, but for non-ideal mixtures it is going to be always complicated. But if it is close boiling, still we can use Murphree tray efficiency in some cases. It is particularly good for the binary mixtures, but in most cases in chemical engineering we are interested in multi-component mixtures. So therefore, we take a more formal approach and develop rate based model. And what we do here now is, until so far we have been looking at the stage J, vapor and liquid together, assuming that the vapor and liquid is in equilibrium. So we have defined something like the composition for the vapor in that phase, the liquid in that phase, but both of them are in equilibrium. But now let's assume that we still have a vapor and liquid, but they are not in the condition of equilibrium, right? So in that case, there is going to be two phases there, let us say a vapor phase and a liquid phase, and there is going to be a mass transfer from the liquid phase to vapor phase or vice versa. Only when the mass transfer ceases, we are going to think about equilibrium, right? In a typical situation, non-equilibrium situation, we are going to have mass transfer of species from one phase to other, right? That is because of the chemical potential gradient, as we will come to that, right? So if we don't have the equilibrium condition, we are going to have a gradient in chemical potential, so there can be a mass transfer. In a similar manner, we can also have energy transfer or heat transfer between the phases, right? So we are going to therefore include the mass transfer rate and the heat transfer rate between the phases, right? Also, we are going to take different temperatures for the vapor phase and the liquid phase. We are no longer assuming that the vapor temperature is same as the liquid temperature in a stage. So therefore, I am going to have different variables for temperature in the liquid and different for the vapor, right? And as we did earlier, we still define the enthalpies for the vapor and the liquid streams separately, and the heat that is removed, I am also writing separately for the liquid and for the vapor. Heat removed from the liquid and separate from that of the vapor. Similarly, the feed to the liquid is taken separate as the feed to the vapor, right? And again, we can define the vapor side stream. This R is RJV is a fraction of Wj by Vj. So these things remain somewhat similar, and this Rjl is going to be something like Uj by J, right? So the fundamental difference, if you have to start thinking about it, is we have to now consider the mass transfer and heat transfer between the phases in a given stage. Okay. So what is going to replace my mesh equations? So now I am going to have material and energy balances separately written for the liquid phase and for the vapor phase. Because the mass transfer is taking place between the two, it is not in a condition of equilibrium. So therefore, the liquid and vapor phase amounts and composition are also changing with time. So therefore, we will write separate equations for the liquid phase and the vapor phase, including the effect of mass transfer and the effect of heat transfer. We will assume phase equilibria only at the interface, right? So now the vapor and liquid, the entire thing is not an equilibrium, but at the interface, I am assuming that there is an equilibrium. Of course, the interface can also move, but at the interface condition, we assume that there is a phase equilibria. That is also kind of an approximation still, but it is a departure from the earlier thing that we assume that the vapor bulk and the liquid bulk was in equilibrium. And now, of course, as I said, we have to include the equations for mass and heat transfer between the phases. We are not going to assume thermal equilibrium, so we don't assume that my TJL is equal to TJV. So they are unequal now, but I still assume mechanical equilibrium because that is typically easier to attain, particularly for things containing liquids, than compared to a temperature or thermal equilibrium, right? And finally, as you will see, I am going to apply the S equations also at the interface in the scheme of things, right? So now the set of equations we are going to have, I am going to label it differently, right? And you will see there are differences in the nomenclature, that you cannot directly use the same E. The E in the mesh equation was referring to phase equilibria, here it is referring to something else, right. So it's entirely new nomenclature which I have added here. It's called MERSHQ equation. The M equation is the material balance is still, but now we have two equations for every stage, for every component. We have vapor phase and the liquid phase material balance for every component. Then we have the energy balance for the vapor and the liquid phase. So we have two energy balances for every stage now. We have, these are my energy balances are E equations. Then we have some R equation for the mass transfer rate between the phases. Then we have S equations still, but applied to the interface. Then we have, in principle, also an equation for the pressure drop once the liquid is going from one stage to the other. There can be a head, and similarly for the vapor there can also be a pressure drop, right. And I can define an equation, H equation, that is a hydraulic equation. In many cases that equation is also not included if pressure drop is not significant, but it is good to consider it when you can imagine that there can be a significant pressure drop in the system. And finally, there is the phase equilibrium again applied at the interface, which I call the Q equation, right. Keep in mind that I am not assuming the equilibrium as a whole again, I am applying equilibrium condition only at the interface, right. The system itself is in non-equilibrium. So, let us go ahead and try to write the equations for this system beginning with the M equations, right. So, again for a stage J, now we have material balance for the liquid phase, material balance for the vapor phase. Let us look at what is leaving from the vapor, what is leaving from the liquid, sorry, what is leaving the liquid. So, what leaves the liquid in the stage J is my liquid side stream Uj and the main stream Lj, and Lj plus Uj by using Uj by Lj as my Rjl can be written as Lj into 1 plus Rjl, right. This multiplied with the mole fraction of component I in stage J. In the liquid phase it is already X, right. So, this is the amount of component I that is leaving from the liquid stream here, right. And then what is entering in the liquid stream is my Lj minus 1. Again, the side stream of j minus 1 I am considering in the balance of the previous stage, right. So, we have Lj minus 1 Xi j minus 1, and now there is a feed separately considered for the liquid phase. So, we have Fijl, that is the component I molar flow rate in the liquid phase entering stage J, and then I have added a mass transfer rate that is basically going away from the liquid to the vapor. That is why I put a minus sign here, and here I am going to put a plus sign for the vapor, right. So, for the time being let us keep it minus, but later on you will see that I mean whatever is leaving from the stage vapor to the liquid, it is actually in one side it is minus, one side it is plus, right, but I will take care of that when I define the mass transfer rate. Okay. So, let us write it for the vapor as well. So, again the first term I had something like the vapor leaving is Vj plus Wj, which I can write as Wj into 1 plus Rjv, where Rjv is my Wj by Vj, and what is entering is my Vj plus 1, right, and there is a feed, the component molar flow rate for component I that is entering the vapor of the stage J, that is my Fijv, and then there is a mass transfer rate, right. For the time being I am keeping it Nijv and Nijl, but keep in mind that they are related to each other, because whatever mass transfer is happening from here to there, negative of that is basically happening in the other phase. There are only two phases there. So, mass transfer is only happening between these two phases. Okay. Now I can write the energy balance equation again for the liquid and vapor separately. So this is my liquid main stream and side stream multiplied by the enthalpy of that. That is what is leaving from the liquid side stream and main stream here. What is entering in the liquid side is my Lj minus 1 multiplied with the corresponding enthalpy. And then what is entering in the liquid feed is now sum over all the species, the component molar flow rate I, that is a net total flow rate Fj entering in the liquid side multiplied by the enthalpy of that, enthalpy per unit mole of that, plus the heat that is removed from the liquid side and the heat that is transferred between the stages, right. Similarly, for the vapor, we are going to have the vapor leaving, that is carrying this energy, minus vapor entering, that is carrying this energy, minus feed entering in the vapor phase, that is carrying this energy, plus the vapor heat added or removed from the vapor, right. Actually, QJV is heat removed from there. So, therefore, I put a plus sign, right, and then minus EJV, that is the net heat transfer into the phase, right. The way we have defined EJV and EJL are net heat transfer into a phase, but keep in mind again, as I said for N, both of them are also related to each other, right. In fact, at the interface, that these two basically should sum to 0, right. So, but the direction is opposite, right. So, EJV should be equal to my EJL, right. What does it include? It includes the convective contributions and the enthalpy contribution. We call it a enthalpy flow contribution, meaning that there will be a bulk flow of species, the entire mixture from one phase to the other. So, anything that is coming along with that bulk flow, that correspond to the enthalpy flow, but in addition you can have extra convection taking place because of temperature difference, right. So, we will write the expressions for that separately, but for the time being what we have done, if I compare with our previous mesh equations for the equilibrium case, is we have added a mass transfer rate and we have added a heat transfer rate, and we wrote the balances separately for the liquid phase and the vapor phase. Okay. Now, we can also write separate mass transfer equations for the liquid phase and the vapor phase. I will write the expressions for that maybe in the next lecture, but for the time being it suffices to say that there are going to be mass transfer equations that defines these rates, and we are writing it not for all the components, because we want to include one equation for the total mass transfer rate, right. Something similar we have done earlier. Instead of two summation equation, we considered only one summation equation and we borrowed another equation from the total material balance, right. Similar thing we are doing here. We have in total C balance, C mass transfer equations we can write, but we write for only C minus 1, and one extra equation we write for the total mass transfer rate. Again, this Nij is going to include the diffusive contributions and the convective contribution that is happening with the bulk flow, and I will write the expressions for that in the next lecture. And this is my equation for the total mass transfer rate, that is entering stage J, right. So, this is basically again what is leaving, that is right here, right. What is leaving, this is the amount that is leaving a given stage in the liquid phase. This is the amount that is entering the stage. This is the sum of what is coming in the feed in the liquid side. I am only doing it for the liquid side, and the sum of the mass transfer rate into the liquid phase. So, this part is coming from vapor, right. Now, when I write it for the vapor, in that case we are going to have what is leaving the vapor, the main stream and the side stream, that is right here. What is entering the vapor is J plus 1, and what is also entering the vapor is the feed, sum over all the component. And then finally, what is also entering the vapor is what is coming from the liquid within the stage. So, this is coming from liquid, and now you see I have put a minus here and plus there, because if there is a net flow from vapor to liquid, then we are going to get a negative term here and a positive term here. On the other hand, if there is a net flow from the liquid to the vapor, then we are going to get a negative term in the down equation and a positive term in the above equation, right. So, but they have to be opposite, because the mass transfer is happening between vapor and liquid phase. We can also write this S equations at the interface. So, we can write for the liquid, the summation of mole fraction at the interface is equal to 1, and also for the vapor in there, right. And then we can write the H equations, the hydraulic equations that correspond to the pressure. So, we say that there is a net pressure drop delta Pj between the stages, which is defined as Pj plus 1 minus the Pj, and we are writing it for 1 to n minus 1, because for the n minus nth stage this Pn plus 1 is not defined, right. So, therefore, we write it only for stage 1 to n minus 1. Those are the number of differences that you have between P1, P2 to Pn. We can have delta P1, delta P2 and delta P n minus 1, right. And the stages, as I said, is assumed to be in mechanical equilibrium. There is a pressure drop between the stages, but the stages itself is in mechanical equilibrium, that is the liquid phase pressure is same as the vapor phase pressure, that is my stage pressure, but the temperatures are not, right. And finally, we have these Q equations, where we assume that the phase equilibrium exists only at the interface, right, and that is similar to the equation that we had, but now it is applied only at the interface of the vapor and the liquid, right. So, now we can do a degree of freedom analysis for this MERSHQ equations. So, we can count how many equations do we have and how many variables we have, and using that we can find the degree of freedom. In this case, we have C equations coming from the liquid phase material balance of all the components, C equation coming from the vapor phase material balance of all the components. We have one total material balance for the liquid phase, one total material balance for the liquid phase, then we have one E equation for the liquid phase, that is the energy balance equation now for the liquid phase, and then we have another E equation, that is energy balance for the vapor phase, and then we have an energy balance at the interface, that essentially means that the heat transfer rates basically cancel, and then we have equations for mass transfer rate. We only wrote C minus 1 such equations, because we considered the entire total material balance separately. And then same thing for vapor, we have C minus 1, again we considered only C minus 1 equations. Then we have a summation equation for the liquid phase for the mole fractions, and we have a summation equation for the vapor phase. And then we have a hydraulic equation, but that is kind of optional. So, if you want to include it, we can, but we may not also include it. And then finally, there is a phase equilibrium, but defined only at the interface, right. So, I am not counting the hydraulic equation. In case we are considering it, then we are going to have one extra equation coming here. Okay. So, then I am sorry, it has to be, I think, n equations, I think one for every stage coming here if we consider the hydraulic one, right. But in total, we are going to have n minus 1 only in the cascade. Okay. So, we can also count the variables. The first variable is the number of stages, right. Then we have the component molar flow rate entering in the feed stream. So, we have C components, n stages, total Nc. Similarly, for the vapor phase, the feed is Nc variables. Then we have the temperatures defined differently for liquid and vapor, right? But then the temperature entering the liquid feed, there are n such values because there are n stages. Then temperature entering the vapor phase, again there are n such values, right? So, you see these variables are getting doubled compared to the equilibrium stage because we are defining separately now for the liquid and vapor, because temperatures of vapor and liquid are no longer equal. We do not have thermal equilibrium, right? Similarly, we have the pressures for the liquid feed, pressures for the vapor feed. The pressure of the liquid and vapor inside the effect is equal, but the feed pressures can be different, right? Then we have n liquid mass molar flow rates. Then we can define again the vapor phase compositions, total Nc of that. Then we can define the ratio of the side stream Xij L. Then we can define the temperatures of liquid in the stage J. Then we can define the vapor temperature, vapor molar flow rate leaving stage J. Then we can define the vapor mole fraction of all the components, again Nc equations. Then we can define the ratio of the vapor side stream to the main stream. Then we can define the temperature of the vapor in stage J, and then pressure of stage J, we are assuming mechanical equilibrium. So, we assume that the pressure is same in the liquid and vapor. So, I am considering pressure together for a stage J, that is my stage pressure. Then we have the phase equilibrium equations for the liquid phase and the vapor phase, right. So, the liquid phase is equated to the interface, and same thing is true for the vapor phase. Let us go back and see, right. So, this can be written for again for the liquid and the vapor, right. And we can write the interface mole fraction, which is defined separately, and the interface mole fractions of the vapor defined separately, right. And then finally, we have the temperatures at the interface, which is also defined separately, and the mass transfer rate, that is defined separately. Keep in mind that I am defining the interface variables separately, right, and that interface is being shared by the vapor and the liquid which is present there, right. So, basically the interface conditions are counted both for the liquid side and for the vapor side of things, right. In the next class, we will do that equations in more detail, right. So, now we can see we can compute the degree of freedom, which is the number of variables minus number of equations, and this particular case it comes out to be something like this. So, with that I conclude the basic formalism of the rate based method. In the next class, we will discuss how we go ahead and basically detail the different terms that we have seen in this particular framework that we have discussed so far. So, with that I stop here. Thank you so much.